Okay, it's time to get back on track here. We are now talking about pericyclic reactions. We spent a substantial amount of time talking about basic arrow pushing, reactions of nucleophilic sigma bonds. We spent some time talking about sulfur and phosphorus chemistry. And then when we left off, I gave you an introduction to 4 canonical types of pericyclic reactions. And we're going to spend a significant amount of time on each one of those. So there's a lot of reading that you can do. This is a very popular set of reactions. So in Carey and Sundberg Part A, there's an entire chapter on pericyclic processes. It depends on which edition of the book you're looking at. So in the 4th edition, you can start reading in Chapter 11, and there's problems at the end of the chapter that you can work. In the Fleming Molecular Orbitals and Reactivity book, Chapter 6 is devoted to pericyclic reactions. And so you can read in those chapters, and it will support the lectures that we're going over. There's an exam on Friday, which is going to cover sulfur chemistry, phosphorus chemistry, and nucleophilic sigma bonds. So I'll have some extra office hours on Thursday. I also have office hours today from 5 to 6, I think. That's what's on the website. And you can feel free to hook up with me then, so we can work through whatever questions you may have. So last week you should have had an opportunity to do some electronic structure calculations. Super important if you're interested in pericyclic reactions or any type of organic reactivity where you want to know something about the energies of molecules, the relative stabilities of molecules, or the relative stabilities of transition states, or if you want to know something about the shape of molecular orbitals. And so hopefully we'll have a chance for you to fall back on your ability to do calculations as we talk about pericyclic reactions. Okay, so let's step into it. So I'm going to talk about 4 characteristics of pericyclic reactions, and this is true for all of the 4 types of pericyclic reactions. And if you want something to think about as I tell you these 4 characteristics, you can just look at this classical Diels-Alder reaction that I've drawn up here. So the first characteristic of all pericyclic reactions is they are concerted, and they involve cyclic transition states. So hence the term pericyclic. So cyclic transition state, if I draw the transition state for a Diels-Alder reaction, it would look something like this. I've got 2 components here, and I would draw partial bond formation here and partial bond formation here. And then there's partial bonding, changes in bonding, cleavage of pi bonds, formation of sigma bonds for the other bonds in the ring. So all pericyclic reactions are governed by principles of orbital symmetry, and we're going to spend most of today's lecture trying to become comfortable with this idea of orbital symmetry. And how do you think about the phasing of orbitals, and how is that important when you talk about pericyclic reactions? All pericyclic reactions, it depends on the substituents, will be stereospecific. And this is primarily because the reactions are concerted and there is not the opportunity for free bond rotation somewhere in a reaction that would normally involve multiple steps. And then the 4th characteristic is not really a characteristic of the reaction, but our representations. And that is that we can draw the arrow pushing either clockwise or counterclockwise, and we will always get the same result. You'll predict the same products whether you start your arrow pushing this way or whether you start it pushing in the opposite direction. You'll get the same result if the reaction is truly pericyclic. Okay, so let's start talking about, well, first, let me offset this by talking about some very similar looking processes that are not pericyclic. So here's an important caveat. So not all reactions that have cyclic transition states are pericyclic. In other words, there are examples of reactions that involve cyclic transition states that are concerted that don't obey all of these simple principles. And it's mainly this principle right here, too, governed by orbital symmetry. Let me give you 2 key examples of reactions that involve cyclic transition states that are concerted and are not pericyclic. And we've already talked about one of these reactions. So I'm going to draw the transition state for a reaction we've already talked about, and that's the Wittig reaction. So the Wittig reaction, we've got some sort of a ylide that simultaneously forms bonds, CC bonds and oxygen phosphorus bonds. So you'll remember, I hope, in the transition state for the Wittig reaction, there's partial bonding to make a four-membered ring. The reaction involves a cyclic transition state, and the bonding isn't equal. But at the time when you're reaching the high energy part of the energy barrier, you only have a little bit of a bond between phosphorus and oxygen, but that's enough. That makes it concerted. So the Wittig reaction is an example of a cyclic transition state, a reaction with a cyclic transition state that is not pericyclic. Let me give you another example of a reaction that is that involves a cyclic transition state. And is concerted, but is not pericyclic. And that's hydroboration. It's one of the first reactions you learn in organic chemistry. And what we'll see is that this can't possibly be pericyclic. Once we break it down into concepts of orbital symmetry, there's no way that this can be a pericyclic process. And yet it's concerted, and it involves a cyclic transition state. So be careful. Be careful about how you use the term pericyclic. Okay, let me talk about what makes, or some thermodynamic considerations for pericyclic reactions. And I'm going to classify the four types of pericyclic reactions, and we'll talk about the enthalpic gain that you get in a pericyclic reaction versus the entropic cost of that pericyclic reaction. So first of all, we'll start off by talking about Cyclo Additions. And I'll draw the canonical 4+2 Cyclo Addition reaction. This is a Diels-Alder reaction, and the arrow pushing doesn't really matter here. The important part is that I'm breaking 2 pi bonds. So I start off with 3 pi bonds, and in the end I only have 1. And I'm making 2 sigma bonds. And if you just look at bond dissociation energies, bonds broken minus bonds formed will tell you something about the enthalpic gain that you have. You would predict something on the order of minus 34 kcals per mole in favorability. It's very favorable to trade carbon-carbon pi bonds for carbon sigma bonds. Carbon-carbon sigma bonds are much stronger than carbon-carbon pi bonds. So all these numbers are in kcals per mole. So that's what you gain enthalpically by doing a simple canonical Diels-Alder reaction. But it costs you to bring 2 molecules together. Actually, the cost of bringing 2 molecules together is not that significant. The cost of bringing 6.02 times 10 to the 23rd pairs of molecules together and pairing all of them up like ballroom dancers, that cost is significant. And when you add up those costs, this cost of T delta S, it's about 14 kcals per mole that it costs you to bring 6.02 times 10 to the 23rd pairs of molecules together. So you gain overall. You have enough enthalpic benefit that it totally outweighs the entropic costs of bringing those molecules together. That's why there are so many examples of Diels-Alder reactions that are used in synthesis and organic chemistry. Now let's compare this to the second type of pericyclic reactions, second class, called the Eeen reaction. And all I'm going to do is I'm going to take one of these pi bonds up here, and I'm going to replace it with a sigma bond. So this is called an Eeen reaction. Everything else is the same. The arrow pushing is the same. And I'm not going to do the arrow pushing. That's not really important here. So that's the Eeen reaction. Now you can see right off the bat I only form 1 carbon-carbon bond. And if you add up the energies here, it's not worth as much. It's now only worth about 17 kcals per mole. Right? I'm not breaking 2 pi bonds, 2 carbon-carbon bi bonds here. I'm only it's only really kind of a loss of one carbon-carbon pi bond. So enthalpically, an Eeen reaction is not worth as much. But the entropic cost of bringing these two molecules together is about the same. The transition state for this pericyclic reaction looks very similar to the transition state for a Diels-Alder reaction. And so the entropic cost is about 14 kcals per mole. These are estimates. And the important part of this is these numbers down here are not that different. They're not that different, right? Just add a little bit of steric hindrance and suddenly this starts to look like it's in balance. Or if you dilute it down, these numbers are for 1 molar reactions. The standard state means 1 mole per liter for all of the reactants. You don't run reactions at 1 mole per liter. You run reactions at 0.1 to half mole per liter or below that. So when you dilute it down, this is even less favorable. The entropic penalty becomes even higher as you dilute things down from 1 molar. So what you find is that in practice, this is not a very favorable process. That's why you see so few examples of Eeen reactions in synthesis, because the entropic penalty is so high and the enthalpic gain is not as good. Usually what you see is retro Eeen reactions in synthesis. So I'm just going to say that this is about the same. Whereas for a Diels-Alder reaction, it's much bigger. Okay, so those are the first two classes of pericyclic reactions. Next is electrocyclic reactions. That would be our next class. And the canonical 6-membered ring form there would be electrocyclic reaction to make a 6-membered ring. Now, what you'll notice is that this is intramolecular. I don't have to bring two components together. And so the entropic cost here is relatively insignificant. If you just go through a bond strength analysis with bond dissociation energies, kind of like the Diels-Alder reaction, there's a trade-off here that's beneficial. And if you do the numbers, this is worth about 17 kcals per mole. And there's no significant entropic penalty like there was in bringing two molecules together in a bimolecular reaction. So you see many examples of electrocyclic ring closures in synthesis. This is a favorable process. Now let me see if I can fit the last example over here. The last class, the fourth of the 4 classes of pericyclic processes. I'll just put about 0 here. It's not 0, but compared to 14 kcals per mole. So this is a 3,3 sigmatropic rearrangement or a cope rearrangement. And if you go through and you look at the bonding here, we break a sigma bond, but we form a sigma bond. We break 2 pi bonds, but we form 2 pi bonds. Obviously, there's no change here. So the net change enthalpically is about 0 kcals per mole, or exactly 0 in the case that I've shown you here. And there is a slight entropic cost here. But I'm just going to say about 0. It's not 0. It does cost energy to bend these things into the transition state. But overall, when you look at the cost here, you would guess that the equilibrium constant for this would be 1. It doesn't favor one side or the other. And the only time you will see examples of these used in synthesis is when you have something to drive the reaction forward. Some kind of substitution pattern that makes this product more favorable, like a substituent here that suddenly makes a more substituted double bond. More substituted double bonds are more stable if all else is equal. So you'd predict this might shift the equilibrium forward. Or if you have some resonance donor or acceptor group there, that would make it favorable. Or if you have the ability for this to undergo some additional reaction that makes it irreversible. Those would be examples of where you'll see sigmatropic rearrangements used, or at least this classical 3,3 sigmatropic rearrangement. Okay, so the most common pericyclic reactions that you'll see, for certain, the Diels-Alder reaction, Cyclo Additions. And you can rationalize some of this based on just thermodynamics as to which ones are most common and which ones are most commonly used in synthesis. Okay, let's talk about orbital phasing. It hasn't really been an issue that much so far in mechanisms, in reaction mechanisms. Chemistry 201 and Chemistry 202. So let me bring you back to a very simple example. So whenever we depict the interactions of frontier orbitals, the interactions of filled orbitals with unfilled orbitals, there's something that hasn't been obvious. And that is whenever you bring two molecules together and you try to depict the frontier orbitals, there are always two arbitrary phasing combinations that you can draw. So let's take an example of a reaction so we can see the impact of having two arbitrary phasing combinations. Let me start off with the arrow pushing depiction. And I'll take an example of some very simple nucleophile. Here's an amine. It's got a non-bonding orbital. And I could make that amine attack an electrophile like methyl iodide. I don't really have to draw that orbital there. I'm really interested in just the arrow pushing, starting from a lone pair and breaking a carbon-iodine bond. And in the process, we'll generate a new sigma bond. Okay, so that's the arrow pushing depiction. Let's look at the FMO depiction, the frontier orbital depiction. And now I'll be really picky about drawing this anti-bonding orbital for the carbon-iodine bond. So I'm going to draw two different depictions here because they're two completely arbitrary phasing combinations. And I'll show you what I mean by that. Let me go ahead and depict this filled non-bonding orbital on nitrogen like that. And then I'll draw this unfilled, empty sigma star orbital for this carbon-iodine bond. And here's the depiction of this anti-bonding orbital. Ooh, that's not what I meant to do. I meant to make the anti-bonding orbital big on the back. And then there's a node in between the carbon and the iodine. And I'm going to go ahead and phase this with some sort of hashed combination here. So that's the phasing. So notice here for this non-bonding orbital, it looks kind of like a p orbital. On one end, I've got unhashed phasing, and on the other end, I've got hashed phasing. And a good phasing combination that would make a bond would be to have like phasing here between these two big ends of these orbitals. That's what's going to lead to a bonding combination and make a carbon-iodine bond. But I could just have equally. There is always an opposite arbitrary phasing combination that you can draw, where you flip the phasing of one of the components. And I'm going to draw the same two orbitals, but I'm simply going to flip the phasing. So here's my methyl iodide, and I'm going to draw this big orbital for sigma star. And I'm going to phase the non-bonding lone pair orbital the same, but I'm going to flip the phasing of the antibonding orbital. And the important thing is this idea of match versus mismatch. What you can see is I'm going to get two new orbitals out of this. One of these orbitals, when these things interact, is going to look like a sigma bond. The other new orbital that you get is going to look like an antibonding orbital. If I mix two orbitals, I'm going to get two orbitals out. So in every arrow pushing mechanism you have ever drawn, you're drawing this phasing combination where things match, where you're forming a bond. Otherwise, you wouldn't have bothered to draw an arrow, a curved arrow for arrow pushing. So you are always representing one of these two arbitrary phasing combinations where you form a bond when you push arrows. Okay, this is important. It's important that you can have some combination of phases that leads to formation of a bond. And that's why arrow pushing works. So let's take an example of a case where things don't exactly work. When we have reactions that have the potential to form two bonds simultaneously, now we have to very carefully consider the phasing of the orbitals. So let's contrast this reaction over here, this SN2 reaction, with a potential Cyclo Addition reaction. And I'll try to pick something that you've never seen before. We'll just take two carbonyl groups, formaldehyde plus formaldehyde. And let's ponder on this potential reaction where I make a four-membered ring. Why haven't you ever seen that before? The arrow pushing seems to work, right? Is that true, that just because we can push arrows that must be a good process? Here's the problem with that reaction, why it is wrong at every single level of detail. What I'm going to do is I'm going to try to draw the canonical orbitals out. If I draw this bond attacking here on this carbon atom, what I need to do is I need to draw orbitals that represent some filled pi orbital interacting with a pi star. That's what that arrow means. This arrow means that this pi bond is a nucleophile, and there is a pair of electrons that's adding to a pi star antibonding orbital. Or I could think about it the other way, this pi adding to that pi star. But I'm going to start at the bottom, where I'm thinking about this arrow. So let me go ahead and draw out. And I'm going to try to draw this edge on here, where I have my oxygen, kind of flat, where I'm looking at this formaldehyde from the edge. And I'm going to try to draw a depiction of this pi-like orbital. And I'm just going to draw the two constituent p orbitals and their relative sizes and their phasing. So if you were a pair of electrons spending your time in a pi-like orbital, you would want to spend your time closer to the electronegative atom. That makes sense. So this is a depiction of pi, of a pi-like orbital. I'm going to phase this the way you phase a pi orbital for a simple alkene or a simple double bond. That's the correct phasing for ethylene or for a carbonyl group, and that's the correct depiction of sizes. The sizes of the orbitals are not important here. What's important is the phasing. Now, that's the filled orbital. There's a pair of electrons in an orbital that looks like this that's going to add to an antibonding orbital, and I'm going to try to draw this other carbonyl edge on. And now I need to draw pi star because we need to add to an empty orbital. And you'll recall that pi star is bigger on the carbonyl carbon than it is on oxygen. And when you draw this phasing depiction, right, if we really want this new bond to form between this oxygen and this carbon, I'm going to phase these so that they're the same. That means I can form a bond here. But the problem is now when I draw the p orbital combination for pi star here, now on this other end, I have the wrong phasing. There is no way that as I form a bond between this oxygen and this carbon, there is no possible way that I can simultaneously form a bond here. I'm going to get an antibonding combination. I'm going to get the opposite of a bond. I'm going to get something that equals breaking of a bond. So let me draw a line here that means bonding formation, and I'll draw a dashed line here I shouldn't even draw anything there. It's a repulsive interaction. It's the equivalent of breaking a bond. So there is no possible way that you could simultaneously form bonds between this oxygen and carbon and this other oxygen and this carbon. You're only going to get to form one bond at a time with those two molecules. And this is why phasing is important. And we refer to this property of orbitals on the same side and phased on opposite sides. We call that orbital symmetry. So these two orbitals, pi and pi star, have the wrong orbital symmetry in order to lead to a concerted reaction. And I'm not going to draw the other arbitrary phasing combination, but if you flip this around, you still cannot form two simultaneous bonds. There is no way to form two simultaneous bonds in that type of Cyclo Addition reaction. Okay, so you've never seen any reaction like this, and you won't see any reactions like this. except under special circumstances, and that's related to orbital symmetry. Okay, so now let's take a look at, I'm going to remind you of something that we covered very early in the course that relates to orbital symmetry, and that is the phasing for the common polyenes. So last quarter, you were introduced to Huckel theory, and with a pen and paper, you can work out the phasing of the common orbitals. So let me go ahead and draw out the three common polyenes. So I'm going to draw this energy, this molecular orbital energy diagram, and this midline here would be just the energy of a carbon p orbital if you don't mix it with anything. And so you might recall that if you take two p orbitals and you mix them together, there's two different ways that you can mix two p orbitals together. One would be a phasing combination, so you get a pi bond. And the other is this anti-phased combination where you'd get the opposite of a bond. So that's pi star. Then when you take a diene and you mix it together, so as you have conjugated polyenes, you start to pinch together the HOMO and the LUMO. I'm going to draw a depiction of the phasing for this, for the HOMO, for a diene. It looks like this. The most reactive pair of electrons spends its time smeared out in this way. The most reactive pair of electrons spends half its time in the shaded area and the other half of the time in the unshaded area. That's the way to think about what that's telling you. So now when I draw out the LUMO, in other words, if you were to add a nucleophile to this, where would that go? And I'm kind of trying to draw this diene edge on here. So this would be a depiction of butadiene. Okay, now let me go over and draw a triene out. And we could draw a tetraene, but that's not very common, actually. I'm just going to draw the three common ones: alkene, diene, and triene. And I'm going to pinch the energy levels down. Trienes are more nucleophilic, and I'm not doing a good job of pinching that, so let me make this energy level higher and this energy level lower. So it's easy. Trienes are more nucleophilic than dienes. And I'm going to try to draw this triene edge on here. And again, I'm going to pay attention to the phasing. And there's really one particular part, even though it looks complex with all of these p orbitals all over the place, there's really only one part of this that I'm going to ask you to pay attention to. And then I'm going to draw the same, and then I'll fill in the phasing after I draw in this triene edge on. Here's the LUMO. And there's a size issue here. I'm trying to say the sizes aren't that important at this stage. Okay, so let me fill in the phasing. And then for the unfilled orbital, the phasing looks kind of opposite. So when you learned about Huckel theory last quarter, there was this idea of nodes where these are on the same face, and then suddenly there's a node here where you have to go to the opposite face to find the same phasing. And the number of nodes increases as you step up in each orbital. The important point that I want to make is if you look at the HOMO here, the carbons at the ends have the same relative phasing. And if you look at the LUMO, they have opposite phasing. Now I'm going to come over here and look at butadiene, and it's different. The carbons at the ends now have opposite phasing. And when you look at the LUMO, the carbons at the ends have the same phasing. And that's different from what we had here. Now when we walk back over to the triene, it's more like the regular ethylene case. So see how in butadiene, these two end carbons, the ones that react in pericyclic reactions, have opposite phasing. Now with the triene, they have the same phasing, the carbons at the ends. And those are usually the focal point for your attention when you're forming bonds in pericyclic processes. And then when we look at the empty orbital, the LUMO, now they're flipped. And if I kept on drawing out a tetraene and a pentaene, adding more and more double bonds and conjugating, you'd see this effect, whereas the HOMO would have same phasing, opposite phasing on the ends, same phasing on the ends, opposite phasing on the ends. I'm not going to draw those out. You're not going to see very many reactions of tetraenes or pentaenes. Really, these are the common ones, and these are the ones you should remember. But if you can just actually remember the first one, you can remember the phasing of the end carbons by remembering that flipping process. Okay, let's see the impact of this. What's the impact of having this, this phasing opposite versus phasing the same, etc.? And that's orbital symmetry. That represents the symmetry of those orbitals, the phasing at those end carbons that engage in pericyclic processes. I'll explain this nomenclature later. So what I want to do is I want to look at the idea that there's different faces to each one of these reactants. So here the idea of a face is maybe not so important, but when I take a butadiene or a hexatriene, there's two different faces, and it is easiest in pericyclic reactions for molecules to approach face to face. So what I want to do is I want to take a 4+2 cycloaddition, and I'll draw this in two different ways. So first I'm going to draw this in the way where this acts as the nucleophile, where the alkene acts as the nucleophile and attacks the diene. So what would that transition state look like if I were to look at the interaction of these two? And I have to I'm trying to draw this edge on so we can imagine that there's a plane to this, and that this alkene is approaching from the bottom of that plane of the diene. So I'm trying to draw this edge on. Okay, so if I'm attacking this diene, that must be the electrophile. I must be adding electrons to the empty orbital. So what did the empty orbital look like? The empty orbital looked like this relative phasing combination here. The empty orbital looked like same phasing. And it's arbitrary whether I draw the hashes on the bottom or the top, as long as I have the same phasing combination on the ends. That's the empty orbital for a diene. That's the LUMO. So if I really intend to attack that, then I need to draw the LUMO for the diene. That means I need to draw the filled orbital for the alkene component. So for ethylene, the filled orbital just looks like pi. And fortunately, this works out. Remember, there's two arbitrary phasing combinations. I can have the hashed on the bottom and the hashed on the top. I'm going to draw it with the unhashed on the top so that I can form a bond here. And now it's totally easy for me to see that if this approaches from the bottom, I can simultaneously form bonds on both ends. The phasing works out. The symmetry of the orbitals is matched. This is a symmetry-allowed process to do a 4+2 cycloaddition. So I've got a filled orbital here, and I've got an empty orbital here. So orbital symmetry works out. But in a cycloaddition reaction, if this is truly a pericyclic process, at the same time that this is doing a nucleophilic attack on the diene is also doing a nucleophilic attack on the alkene. In other words, I also need to think about this opposite process where I take the electrons in this filled orbital and attack the empty orbital here. So let's draw out that depiction. If we draw out the filled orbital for a diene, let me try to draw that kind of distorted so it looks kind of edge on here. I'll try to flatten it. There we go. Okay, what about the filled orbital for a diene? What does the phasing look like for that? In other words, if I'm using the diene as the nucleophile, then I need to draw the phasing like this. And so let me draw that phasing. So the filled orbital, the HOMO for a diene, has this opposite phasing on the end carbons. And if I'm attacking an alkene, I'm adding to pi star. And there's two arbitrary phasing combinations for the pi star of ethylene. And I'm going to draw the one that matches, where this is unhashed and this one is hashed. So this simple diagram that we've drawn here using Huckel theory explains why a Diels-Alder cycloaddition can be concerted and pericyclic. At the same time that I'm attacking on this end, I can simultaneously form a bond on the opposite end. Each one can act as a nucleophile, and in each case the orbital phasing works out to explain how you can simultaneously form two bonds at the same time. So that's a symmetry allowed process. It's allowed by orbital symmetry. The phasing matches. Now, I'm not going to ask you, I don't think I'm going to ask you any questions about butadiene in this course. Nobody cares about the Diels-Alder reaction between butadiene and ethylene. You care more about reactants that have substituents and weird substitution patterns. And so let's make an important point. So let me take a more interesting case, maybe slightly more interesting. Let's suppose I take a hetero Diels-Alder reaction where I take away a carbon atom and I replace it with a nitrogen atom. What's going to change about this analysis here? If I take out a carbon atom and I replace it with a more electronegative atom, first of all, the energies of the orbitals will change. If I replace carbon with a more electronegative atom, every single orbital that involves that atom will drop in energy. If you were a pair of electrons, you would want to spend your time in an orbital that involves an electronegative atom. That makes sense. But the importance is when I draw this, this depiction of these orbitals, and I'm only going to take the case where I draw the filled orbital for this. Actually, this seems kind of weird because that looks like an electrophile to me, but it doesn't matter for a pericyclic process. So let's take an example where I take this combination of pi-like components. I'm going to change my butadiene to this imine, and I'm going to change my alkene, my dienophile, to this carbonyl group. And the importance is, even though it distorts the shape of the orbitals, if I draw the empty orbital here for a carbonyl, it's bigger on the carbonyl carbon than it is on the oxygen. And you have opposite phasing here. So in other words, replacing carbon with oxygen distorts the size of the orbital on each atom, but it doesn't change the phasing, this flip in phasing as you go from one atom to the other. So the sizes of these orbitals change, but not the relative phasing. That's what happens as you replace atoms and add substituents. And if I replace carbon with nitrogen here, the relative sizes of these orbitals change. Right, if I think about the filled orbital, if you were a pair of electrons, you'd want to spend your time near nitrogen. That's electronegative. That makes sense. So now when I fill in the phasing, it's going to look the same for the HOMO for butadiene. So the relative sizes of the orbitals change as I change from carbon to oxygen or carbon to nitrogen, but the phasing stays the same. So you can still have a concerted process as you pluck out carbon and replace it with oxygen, or if you put substituents on the fringes of these molecules, the phasing, whether it's hashed or unhashed, will stay the same. So in other words, you can still use your simple model of ethylene and butadiene and hexatriene to think about whether reactions will be concerted or not. Okay, there's two different faces to these molecules, and in this case it really doesn't matter. There's a top and a bottom face. And so let's think about how that might impact the approach of two molecules as they approach each other. So let's think about this as a pericyclic process. Two dienes coming, right? I can draw perfectly good arrow pushing that has arrows going all the way around in a circle in an octagon shape. I don't even know how to draw this arrow here. I just want to pretend we're using this as the nucleophile and that's the electrophile. So this is not like regular arrow pushing. So if the bottom one is the nucleophile, then I need to draw the HOMO for butadiene. And so let me phase that. And the HOMO for butadiene, I've got two on top and two on the bottom, and there's a single node where it flips, phased on top, or hashed on top, hashed on bottom. So that's the HOMO for butadiene. And if I'm attacking butadiene, I need to draw the LUMO for butadiene for that top molecule. So if I'm putting electrons into an empty orbital, and what I'm trying to imagine here, and it's not, I have to try to depict this, is this sort of edge-on approach here, where these molecules are coming face to face, or they're approaching face to face. Where the bottom face of one molecule is approaching the top face of the other. And I have to choose the right phasing for the LUMO of butadiene. So the LUMO of butadiene, I want to have some sort of good phasing combination here, right? I want to form a bond, so if I have a choice, I'll draw the hashed phasing here. That's good. But in the LUMO, there's a problem, and that is that the other end has the same phasing as the end over here. And so I can't simultaneously form a bond, and I don't know how to do this. I'll just put a little thing here. You get the equivalent of an anti-bonding combination on the other side, the equivalent of breaking a bond. So there is no way to do a simultaneous 4+4 cycloaddition if the two molecules approach face to face. You can form a bond on one side, but if you do that, you'll end up forming an anti-bond interaction on the other side. Okay, so there's no way to do a face-to-face 4+4 cycloaddition. That doesn't work. So how could we twist this around or distort it so that I had hashed phasing combination somehow interacting with this bottom phase? How can I make it so that this top molecule simultaneously interacts with both the top and the bottom face of this molecule? In theory, there are ways you can distort the approach to make one component, like this bottom component, react on opposite faces simultaneously. But you have to come up with some creative, let's try to depict that. It's possible, hypothetically, to make them approach in that way. And this is kind of the trickiness of trying to draw something on a two-dimensional blackboard. I'm going to try to draw an approach of those two molecules that would allow, I'm going to try to draw this diene edge on. I'm trying to make it look like you're looking at the edge of this top diene. And in order for me to make two different faces, here and here interact with this, I somehow have to take this molecule and twist it. So one face of this molecule can interact here, and the opposite face can interact with that side. And there is a conceivable way to arrange that to make that work. And I'm not saying that this is a very favorable reaction, but I'm going to try to draw it so that now two different faces of this can react. So now one face of this diene can interact here, and the opposite face can interact with this other carbon. So let's go ahead and draw in that phasing. Let's draw the LUMO here. Now I want to make the phasing the same that I... And now I'm just going to draw the phasing on the end carbons because that's all that really matters. So if this is the nucleophile, if this is the HOMO, how would I make that interact? Well, what I would do is I would draw this back carbon interacting and forming a bond. And now when I take this other carbon that's in front, how do I make this look like it's in front? I don't know. Maybe I'll make it darker so it looks more like it's in front. You'll remember for the HOMO, I've got the opposite phasing combination. So if I tilt this, it is conceivably possible I could make this bottom component, the nucleophilic, what I've drawn here is the nucleophilic component, react on opposite faces simultaneously. It is possible to have such arrangements of molecules. Okay, what's the problem? The problem is that it costs so much. You have so much banging of hydrogen atoms when you adopt this kind of transition state that this reaction will never compete. In other words, why haven't you seen this kind of 4 + 4? Because it's way faster to do this. Right? You're never going to outcompete that. It's not to say you can't hypothetically, if you draw this in a computer, get this to form bonds. But when you put them in solution, this is always going to be much faster than that. That's why you've never seen a 4 + 4 cycloaddition. It's not impossible. It's just not. There's always going to be something better and faster. Okay, I called that a 4 + 4. Let's talk about nomenclature for cycloaddition reactions. Oh, let me give you two pieces of language to describe that, this interaction here. I forgot to give you those two pieces of language to describe that. We have a way to describe these two components. We would describe this top molecule as reacting in a suprafacial manner. So this is an adjective that describes a molecule that simultaneously forms bond on a single face, like simultaneously on the bottom face or simultaneously on the top face. So both ends react on the same face. And the opposite of that would be a reactant or a component that reacts in an anterofacial manner. So on opposite faces that simultaneously reacts on opposite faces of the molecule, of the pi system. So the two components can approach each other in a suprafacial manner or an anterofacial. One of the components can be anterofacial, as I've drawn here. Now, it's usually easier to adopt geometries where things react face to face. It doesn't require any weird distortion of a planar pi system. Pi systems tend to be planar. Okay, so let's talk about this nomenclature. I've referred to 4 + 2 and 4 + 4. And I want to contrast two different types of nomenclature for pericyclic processes. Okay, the most common nomenclature that's used for pericyclic reaction is the atom counting nomenclature, where I have two components that react with each other. One that has M atoms and the other that has N atoms. This is very simple, 4 plus 2. A Diels-Alder reaction is a 4-atom component plus a 2-atom component, and the ring size is the sum of those. So let's take an example. If you think about what a 6 plus 4 cycloaddition would look like, it would look something like this. I'd have a 6-atom component. There's a 6-atom component. And I'd have a 4-atom component. And I'm going to put some substituents on here so you have actually a real example. That's cyclopentadiene. And this is a 7-membered ring called tropone. It's a cyclic ketone called tropone. And I'm not doing a good job here, but cyclopentadiene. So these can undergo a 6 plus 4 cycloaddition reaction where you simultaneously form bonds between these two carbon atoms. You can also have 4 plus 3 cycloadditions. Right? You just need to have an allyl component, either an allyl anion or an allyl cation or some heteroatom equivalent of those. So if I take an allyl cation and you looked at the orbital phasing, it would predict that this is completely possible to do this in a superfacial manner. You can simultaneously form bonds. So we would call this a 4 plus 3 cycloaddition. I won't write cycloaddition here. It's possible to have something like a 2 plus 2 cycloaddition. Hopefully I'll get a chance to comment on this further. And I'm running out of room here, so I didn't do a good job of organizing my space. I'll just call this an Alder-Eeen reaction. So you'll remember an Eeen reaction is kind of like a Diels-Alder cycloaddition, but we replace one of the pi bonds with a sigma bond to a proton. And in the Alder-Eeen reaction, one of the components is a ketone. And you can simultaneously form bonds here. Okay, so this is one type of nomenclature. This is the most common type, and it works really well for cycloadditions. Remember, thermodynamically, cycloadditions tend to be thermodynamically favorable. So you'll see lots of examples of cycloadditions, and this is a very convenient nomenclature for describing cycloadditions, which are the most common type of pericyclic reaction. But there's another type of nomenclature that's used that describes the pi electrons. So instead of atoms, actually let me try to put it here. There's another type of nomenclature that describes electrons. So let me try to give some sort of a description of the less common nomenclature. So a less common nomenclature makes some attempt to break each interaction down into a description of the pi electrons based on Huckel theory. So I've got a 6-electron component here. This looks kind of like hexatriene from Huckel theory. So I would refer to this as pi 6 suprafacial. This component has 6 pi electrons. And you can't tell because I didn't draw it 3-dimensionally, but it could react superfacially. And it's reacting with a 4 pi component. 4 electrons, pi, suprafacial. So this would be a different way to describe this process. Obviously, it conveys a lot more information because it tells you about the faces of these as they interact and the number of pi electrons, not just the number of atoms. I would describe this as a 4-electron plus a 2-electron process. There's only 2 electrons in an allyl cation. And these are both pi components. And it works when they're both superfacial. Over here, this is a very special reaction. This involves two electron components. One of these has to react antirofacially because you can't have a simple 2 plus 2. We already talked about that. And the other can react, one has to be antirofacial and the other has to be superfacial. And then finally I come over here and it's not all the electrons are not in a pi system anymore. I've got pi electrons, but this is a sigma bond and it has to break. And I'm going to form a new sigma bond over here. So the correct description of this would be 2 electrons plus 2 electrons plus 2 electrons. And one of them is a sigma bond, and it's superfacial. The other is a pi bond, and it's superfacial. And the other is a pi bond, and it's superfacial. Now I'm guessing none of you have ever seen this bottom nomenclature before. I'm guessing. It's very sophisticated and it's very powerful. But since the most common reaction that you see used in synthesis are cycloadditions, and this works so well for explaining cycloadditions, you very rarely need to fall onto this nomenclature down here. So you'll tend to see this used very frequently. And I'm going to make one last point, is that this nomenclature that's used on the top here is often used for non-pericyclic processes as well. So you have to be careful with that. Let me give you an example just before we leave here. So just because somebody calls something a 4 plus 2 cycloaddition doesn't mean it's pericyclic. So here's an example of a reaction. That involves 3 kinds of components. And it's definitely stepwise and not pericyclic. If you had a cobalt catalyst to this, you can make a new 6-membered ring. And it involves, the mechanism involves many, many steps. And without question, the mechanism for this reaction is not concerted. And you will see this type of thing in the literature referred to as a 2 plus 2 plus 2 cycloaddition reaction. And that does not mean that it's pericyclic. It's simply a way, this same nomenclature is often used, because it's very useful, is often used to describe stepwise processes as well. This is definitely not a pericyclic reaction. Okay, I'm going to stop right there. When we come back, I'm sorry I went a little over on my time. And when we come back, we're going to describe substituented effects and what differentiates fast pericyclic reactions from slow pericyclic reactions and how you can rationalize that.